Welcome back, Marauders. In this video, we're going to review how to figure out if a molecule is polar or non-polar. For a molecule to be polar, you have to have two things. You have to have polar bonds, and you have to have a geometry where it doesn't get canceled out. So looking at this first example right here with CO2, carbon dioxide has a polar bond. Oxygen and carbon, they have different electronegativity, so they don't share the electrons equally. Oxygen gets a partial negative charge, carbon gets a partial positive charge, so it has a negative side and a positive side. However, carbon dioxide is a linear molecule, so you end up with a partial negative over here on this oxygen, and exactly opposite that, 180 degrees away, you have a partial negative on this oxygen. And so since that's a symmetrical molecule, it cuts right down the middle, it's the same on the left and the right, it ends up being a non-polar molecule. So it has polar bonds, but it ends up being a non-polar molecule because the geometry is symmetrical and it cancels out those polar bonds. So what you have to do is look at two things. You have to look at, does it have polar bonds? And then what is the molecular geometry? Does it cancel it out? As far as the shapes, all of the molecular geometries that are the same as the electron domain geometry, so that means there are no non-bonding electron domains. There's no extra electrons here. There's no extra non-bonding electrons here on a trigonal planar molecule. Same thing, tetrahedral molecule. Those are all have zero non-bonding domains. Then those are always going to be symmetrical molecules. Okay, so if you have a linear, trigonal planar, or tetrahedral molecule, they have zero non-bonding domains, and so they're going to be symmetrical. And so the linear, trigonal planar, and tetrahedral are always going to be non-polar. That's assuming that they have the same thing in each one of the corners. So like in here, you have hydrogen, 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 hydrogen. They're all the same. It could become a polar molecule if you had like hydrogen, 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 and then a chlorine attached over here. But if you have the same thing at each one of those points around the central atom, then it's going to all cancel out because it's a symmetrical shape. And then typically the ones that have non-bonding electron domains, so you have a non-bonding electron domain, non-bonding, two non-bonding electron domains here, that makes the shapes asymmetrical. And when they're asymmetrical, then the dipoles of this polar bond don't get canceled out. So think about like water. Water has this polar bond, and it's an asymmetrical shape. The two hydrogens down here, there's nothing up there above them to cancel them out, so that ends up being a polar molecule. So typically, the ones that have non-bonding electron domains, the bent, the trigonal pyramidal, the bent coming from the tetrahedral shape, those are all going to be polar molecules. Let's look at a few more shapes with the trigonal bipyramidal and octahedral geometries. So same thing as before, when you have zero non-bonding domains, so the molecular geometry and the electron domain geometry are the same, then it's going to be a symmetrical shape and the molecule is going to be non-polar. Even if those are polar bonds, they're all going to cancel out because they're exactly opposite each other. So this one and this one are opposed to each other, and so they cancel each other out, and then these three across the middle cancel each other out. Same thing down here with the octahedral shape. So it's a symmetrical shape. It's going to be a non-polar molecule, assuming that all six of those atoms around the outside are the same type of atom. Then generally when you have non-bonding electron domains, it's typically going to make this shape asymmetrical. So like a seesaw shape is asymmetrical. The T shape is asymmetrical. The square pyramidal shape is asymmetrical. So those asymmetrical shapes, the seesaw, the T shape, and the square pyramidal, since they have differences on the two different ends, then it would become a polar molecule. There's a couple exceptions to that. So here with the linear, we have three non-bonding domains, and when you take away all three of those, then it ends up being a symmetrical shape again. So this linear molecule would end up being non-polar because these two dipoles would cancel each other out. And then the same thing down here with the square planar. Even though you have two electron non-bonding domains, they cancel each other out, and the remaining square planar shape is symmetrical, and so that would be a non-polar molecule as well.